we present QUASAR, a quad-based scene approximation and streaming system designed for remote rendering. Remote rendering offloads intensive graphics tasks over a wireless link from thin clients to nearby edge servers. While this setup enables high-quality rendering, it introduces latency due to round-trip data transfers. In a typical pipeline, the client sends its pose to the server, which receives it after a short delay. The server then renders the scene and transmits the results back to the client, arriving after an additional delay. By the time the result is displayed, however, the user's pose might have changed, leading to a visual mismatch between the rendered content and the user's actual viewpoint. This mismatch creates a noticeable visual lag that breaks immersion and can cause user discomfort, nausea, or even motion sickness. To mitigate this, image-based rendering techniques are often used to mask latency. One common approach is planar warping, where the rendered image is transformed using a homography to match the new viewpoint. While effective in reducing perceived lag, planar warping introduces smearing artifacts, especially at image boundaries. More importantly, it only handles rotational differences and lacks motion parallax, a crucial depth cue. To address this, systems can transmit depth maps to the client, enabling reconstruction of a 3D mesh that approximates the scene geometry. This method, known as mesh warping, allows for some motion parallax by reprojecting the image onto the mesh. However, mesh warping has its own challenges. It often introduces rubber sheet artifacts around object edges and can generate high-resolution meshes that are expensive to render on resource-constrained devices. Mesh warping fails to capture disocclusion events, which occur when previously hidden regions become visible due to camera motion or viewpoint shifts. The black regions in the top video represent unhandled disocclusion events, which are essentially holes in the reconstructed geometry. While some techniques attempt to fill these holes, they cannot recover the actual scene content. For example, a gold coin hidden behind a robot arm, highlighted by a red arrow, remains hidden in the warped image, showing the importance of capturing disocclusions, especially in interactive scenarios like VR gaming or training, where missing visual cues can affect gameplay or performance. To overcome this, the system must identify geometry that could become visible in the near future and transmit it to the client ahead of time. This leads to a split rendering architecture, where shading and geometry processing are decoupled, allowing novel views to be rendered locally on the client. Rather than transmitting full scene geometry, which is bandwidth intensive, we selectively send geometry based on potential visibility from future viewpoints. We can formulate this problem as follows. Upon receiving the client pose, the server must predict the future pose the client will occupy by the time it receives the rendered result. The server can use pose prediction to estimate the future pose, but this estimate can be inaccurate at high latencies. Instead, the server can define an uncertainty volume, a region centered around the predicted pose, that encompasses where the client could potentially be. The server then only needs to determine and transmit geometry that is visible from all viewpoints within the uncertainty volume, also called the view cell. To stream geometry efficiently, we avoid sending raw triangles, as they are bandwidth intensive, offer limited shading flexibility, and don't degrade well under fluctuating network conditions. Instead, we use a proxy representation that enables high-quality rendering while consuming less bandwidth and adapting more gracefully to network variability. Prior work has explored this concept. For example, QuadStream uses compressed quads to approximate scene geometry. Starting from a G-buffer, QuadStream fits a series of quads to a given viewpoint. Each quad is initially fitted to a pixel, and adjacent quads are progressively merged to improve efficiency. To handle disocclusions, QuadStream samples views from corners of a box-shaped view cell, and masks visibility using existing quads. While effective, this approach still requires high bandwidth and does not scale well under latency or network variation. Our goal is to create a streaming system that provides high-quality shading and withstands high latencies without sacrificing bandwidth or compute. Homography-based time warping produces smearing artifacts at high latencies and fails to capture motion parallax. Depth-based warping produces smearing artifacts at object edges and does not capture disocclusions. Geometry streaming systems are bandwidth intensive and can produce blurry image regions. Quad proxy-based systems like QuadStream can provide high shading rates but still require high bandwidth networks. Our system, QUASAR, builds upon and improves the quad-based representation introduced by QuadStream. It builds on the key advantages of using quads as geometric proxies, like high shading performance, ease of processing, and strong compressibility. To make quads even more streamable, we introduce an improved method for disocclusion coverage, a temporal compression technique, and ways to reduce the overall quad count for smaller data sizes. Our first improvement targets disocclusion coverage. Instead of adding more views, we cleverly peel away occluding fragments to reveal potentially hidden geometry, fitting quads to layers rather than individual views. This strategy captures disocclusions with fewer quads, allowing for merging within layers and reduced overall quad count. Additional layers can be added to cover smaller disoccluded regions. Finally, like quad stream, we expand the field of view during quad fitting to capture content beyond the current frame and minimize out-of-frame artifacts. By combining all depth peeling layers, QUASAR clients can render novel viewpoints with disocclusions accurately reconstructed. A major portion of the data payload, often over half, comes from the initial visible layer. To reduce this, we leverage the spatio-temporal stability of scene geometry. Since much of the environment remains static over time, we transmit only geometry that has changed since the last keyframe. To illustrate, imagine we begin with this set of visible quads from a camera view. As the scene updates over time due to animation, we track which parts of the geometry have changed from the previous reference view. Under novel viewpoints, previously unseen geometry may become visible and must be captured. To capture disocclusions, we fit a new set of quads to the newly revealed geometry. Rather than sending a new set of yellow quads, we only send the green and magenta. This dynamic tracking enables us to reconstruct live animated scenes in real time using a compact set of quads. To adapt to changing network conditions, QUASAR provides graceful degradation controls. Geometric complexity can be tuned on the fly by adjusting the degree of quad merging, trading off between accuracy and data size. Likewise, the view cell size can be scaled based on network latency. Larger view cells improve disocclusion coverage but require more data, while smaller view cells reduce transmission costs at the expense of completeness. We now demonstrate that QUASAR frames can be rendered in real time on a mobile GPU. We show actual screen captures recorded on a Meta Quest 3 VR headset. Finally, we present comparisons of QUASAR against state-of-the-art methods. These comparisons show that QUASAR maintains high visual fidelity while using significantly less bandwidth, particularly under challenging environments. First, we show comparisons under low latency conditions. Now, we show comparisons under high latency conditions. If you're interested in trying out Quasar, scan the QR codes to access the webpage and the code. We provide a lightweight testbed for exploring algorithm parameters and comparing baseline methods. Thank you for watching, and don't forget to like and subscribe.
QUASAR.